Hello, welcome back. And in this video, we are going to be looking at our Lru Cache implementation. Okay, so let's go ahead and get started. I'm going to create a new file here, and we're going to call this one Lru Cache.swift. Right. First thing we're going to do is we're going to import Foundation because we are going to need some of the basic things from Foundation. And because this is a cache, we're going to use generic to build this cache so we can, depending upon the nature of the data, we can store any kind of data into this cache. Okay, so we're going to create a class Lru Node, and this is going to be the node that's going to be keeping all the information. And it's going to take two values, key and value. And we can create our key of type K and value of type V. We also need to create our next pointer, so Lru Node, and previous pointer, Lru Node. Okay. Now we're going to initialize, and in our initializer, we are simply going to take key and the value and then we're going to say self.key is equal to K equal to key, self.value is equal to value, self.next is equal to nil, and self.previous is equal to nil as well. Okay, so this is our node. This is the node that we're going to be using in our Doubly linked list. All right, so let's go ahead and create our Doubly linked list. Now we're not going to create the full implementation of Doubly linked list because not everything is needed. Excuse me. Not everything is needed for our use case. So what we're going to do is we're going to focus on specific aspects that fulfill the requirement of building this cache. And this happens all the time in the real work environment, where if you need to build out a custom data structure, you're not going to build out the each and every functionality that's out there that's written for the algorithm or data structure, like in the definition. What you build out is what you actually need and what's needed to support your own custom data structure. That's why we actually learn all these data structures, so we can understand how we can pluck those things out that we need and leave everything else as is. Okay, with all that, let's go ahead and create our Doubly linked list. So I'll just say D-link list, like so. And once again, this is also going to be generic. So we're going to take the same key and value pair, and we're going to create our head node. With key and value, and our tail node, not Lru Cache actually, it's going to be Lru Node. Key and the value. There we go. Okay, we can just provide an empty initializer, and these two we can make them optional. Okay, now let's go ahead and start our functions. So first function that we need is basically add to head. So basically when we get a new item, right? So either we are getting a brand new item to be inserted into the cache, or we are actually removing an item from the cache, from somewhere in the middle of the cache, and moving it to the front of the cache. Those two operations are gonna be needing this add to head function, which is gonna add the element to the head of the list. Okay, so let's say add to head, Lru node and takes the generic Lru node, and basically you can simply now start checking for things. So first thing you're going to check if self.head node is not equal to nil, right? So basically fetch the head node and basically see if it is not nil. That means there's something in the list. Now, if there's something in the list, that means you're going to keep that head pointer into a temp variable, and then basically take your newly provided node that you have and make that your head, and then this newly provided head next is going to be point to the old head, which is stored in the temporary variable. Okay, so once again, we're going to create a temporary variable and store our head node into that. Then we're going to say temp dot previous is equal to going to be node, right? Remember, this is doubly linked list, so previous pointer is also there. Then you have self dot head node is equal to node, right? So your new node, the newly inserted node becomes your head node, and your head node's next becomes your temporary pointer that you have stored. Okay, so that's how you are going to insert the item at the head when list is not empty, and you return from here. Otherwise, if you proceed from here, excuse me, if you proceed from here, that means that your head is actually nil. That means your list might be empty. So you simply say head node is equal to node, and you also want to point your tail node to node as well, because your list is empty and you need to point both head and tail to the same value. All right. So with that said, our head node implementation, add to head implementation is complete. Now we need to talk about this remove functionality. Okay, so let's build remove node. And once again, we're going to take the node, key and the value, and we're going to start checking. So first thing we're going to check if self.head node is not equal to nil. Okay, and we're also going to check if self.head node and unwrapped that. Okay, so basically get the memory address and triple equal. Now this is new to Swift. I think this was Swift 5.1 when it was introduced. Basically, triple equal means that you can compare the memory addresses for these two objects and say if they're pointing to the same memory address or not. So that's what this comparison means. So what we are saying is, if the head is not nil and the head node is pointing to the same memory address as the node that's provided, that means what we are trying to remove is the head element, right? In that case, we're going to simply say if self.head node dot next is nil, right? So if the next item is nil, this means the head node is the only node in the list. So we simply say self.head node is equal to nil, and self.tail node is equal to nil. Okay, so that's our first check. Now, if the next is not nil, right? This is the else condition for when next to item to head is not nil, right? So what happens here? Okay, so what are you gonna check here? So when your list is not empty, right? This means that head needs to be assigned to the next element to the head. Okay, so So we're going to say self.head node, self.head node dot next, and self.head node dot previous is equal to nil. Okay, why is that? Because remember, the next item of the head node is going to have the previous pointer, which is still going to be pointing to the old head. So you want to make sure after you assign your next element of your head node's next element to the head node, you make sure you basically just nullify the previous pointer so it becomes the real head node, and the node that you're trying to release is released from the memory. It's actually ready for garbage collection or anything like that. Okay? Or its reference count goes to 0. All right. So that is our if and else conditions for when the head node is not nil and the head node is the one that we are trying to delete. Else, if node dot next is not equal to nil, that excuse me. So what this means, this condition means that we are trying to delete something that's in the middle of the linked list. Okay. Now remember, this is doubly linked list, and we already have the address for it. So we simply need to do is we need to take that node's previous node. We go to the previous node. So let's say if you have these 3 nodes and you're trying to delete this one, what you're going to do is you're going to go to this node, and this node's next is basically, right now it's this middle one. So you're going to take its next and start pointing to the last one, right? And take this node's previous and point it to the first one. That actually removes the middle node completely out, and these 2 nodes are pointing at each other. Okay? So with that said, the implementation is very simple. You simply say node dot previous dot next needs to be node dot next, right? And node dot next dot previous is going to be node dot previous. Okay, so that is going to get rid of the middle element that's there. Now, if none of these conditions are true, now if we reach here, that means we are at the tail node of the list. And removing the last element means that only the previous item of the last element is the one that's going to become tail, and after that, its next is going to be pointing to nil, and that becomes your new tail. Okay, so basically you take node and you say node dot previous, right, dot next becomes node dot next. So if it becomes nil, I mean it's already no, it's actually so node dot next is going to be nil in this case. So anyways, you can either type node dot next or you can type nil. Nil is more clear. Then you take this self dot tail node and you say node dot previous becomes your tail node. Okay, and that gets rid of your tail node that was there, and then you have actually removed it, and previous node to the tail becomes your new tail. Okay, that's the implementation for our doubly linked list. Now, let's take a look at how we're going to take all of this and create an Lru cache. Okay, so let's create class Lru cache, and this one is going to be taking key. Key needs to be hashable, and value. So these 2 generic properties we are providing. Now remember, we talked about capacity, so that's one thing that we need to actually count for. So capacity, all caches need capacity. So every single cache that you create, it needs to be memory bounded, so it just doesn't grow to infinity. Okay. Then you're gonna actually keep a variable to count the length of your cache. Okay. And then these two can be private, and we'll make them public as we needed. Okay, so we're gonna create a queue, and queue is gonna be a doubly linked list, or D linked list in our case, right? And this D linked list is gonna be of type same generics that's been supplied to the Lru cache. Okay. You're also gonna have hash table, and this hash table is simply a dictionary, and this dictionary is going to keep the key itself, okay, and the address for that node. So we can actually remove it from our doubly linked list or from our queue. Okay, this is iOS, very iOS specific dispatch queue. We're going to use dispatch queue to dispatch all these feature functionalities and make sure that this particular operation or these operations are thread safe. So we're going to create dispatch queue, and it's going to be of type dispatch queue. And you can have any label you want. Okay, Lru Cache. All right. So now it's time to init, and let's initialize our cache. We're gonna only accept the size. We wanna know during the initialization what size of cache you're gonna need, and we're gonna assign that to capacity. We're gonna take our length, and we'll say it's 0. We'll take the queue and initialize that. Okay, and we take our hash table and simply initialize that with minimum capacity as well. As size. Okay, and those are all the initializations. Now let's create a subscript so we can start looking into how we can access values of the cache. So subscript, and subscript takes basically it's going to expect a key to be supplied of type K, and it's going to return a value optional B. There you go. Okay, so subscript takes get and set. Set gives us a value that we can set, and get actually gets the item, right? So subscript, in case if you're wondering what it is, if you're dictionary D, you do just square bracket and you type your key, that's the subscript. Typing the key and this format is basically the subscript. That's how we are designing our Lru cache. Okay. So first we're gonna create our node, and this node is gonna be Lru Node. Okay, and we're gonna use our dispatch queue. And we're gonna make this a sync operation. Okay, and we're going to say node is equal to hash table key, right? So we'll try to retrieve that node from the hash table, okay, depending upon the key. So the key is given. We are doing a lookup operation. It's saying, is there any value like that in the hash table? If there is, then return the memory address for that particular node. Okay. If the node is not equal to nil, right, that means there's something, then we simply take our queue and we say remove that node and add it to the head. So we started moving that node and removed it from the list and moved it to the head. Okay, and our remove node will take care of, like, if it's at the head and stuff like that, and add to head is going to take care of, like, how it needs to be inserted. So we don't have to worry about those things, right? So that's all we need to do in here. Now, once we are done with this operation, we're gonna say if node is still nil, right? So this operation is gonna return from here if node is still nil. Otherwise, we simply return node dot value. Okay. So what's gonna happen is basically your item is looked up in your hash table. Okay. And this is the lookup operation. So your item is looked up in the hash table. If you found the address for the node, you simply move that node into the front of the queue, and then you return its value. But during this operation, if you didn't find that particular item in the cache, that means you simply have to return nil. Okay, so that's what this is doing. Now let's go ahead and build our set functionality. So set is basically setting the value, or setting the value for this cache. So we are simply going to first say dispatch queue async, and then we need flags. Once again, this is iOS specific, a barrier flag, and I'm going to say if the value that we have been provided is nil, we simply return from here. Okay. Now, if it's not nil, then we need to check if we can create a node out of this, or if we get the node for this particular value in from the hash table. So we do our lookup, and we say, like, hey, we found the value. We simply say node.value is equal to the new value that's been provided. Okay. And then once we have updated the value, so basically this is, so let's say you had an item that stored 1, and now you want to set 2 for that item. You can simply provide 2, and we can update that value for that node, and then we're going to simply say remove node and add to head, like that. Okay. If that is not the case, okay, so if our item was not found in the cache, in that case, we're going to create our node with key as whatever the key is provided, and the value is the value that's been provided. So we have both of these informations, and we are simply going to say that if first we're going to check if the length, if self.length is less than self.capacity, right? So we are still in the memory limit. Then we simply say self.q dot add to head, okay, and we supply our node. If that is not the case, then we need to, sorry, I'm going ahead. Um, let's finish this. So we added our item into the queue. Now we also need to add our item into the hash table with the key and the value to be the node. So they both are going to start pointing to the same memory address. And we increase our length by 1 plus equal 1. There we go. Okay. All right. Now, if that is not the case, the first thing we need to do is we need to remove a value from the hash table. Now, what we're going to remove is basically, first, we're going to remove the tail item. So we're going to get the tail item. So tail from the queue, right? So we get the tail node from the queue, and we say get me the hash table and remove value, right, for key, and we supply the key as tail dot key. Okay, so that actually is going to remove that particular item from hash table. That's first operation. Then we simply say self dot q dot tail node is equal to self dot q dot tail node dot previous. Okay, so we're going to start taking the tail node and we're going to start pointing the previous node of the tail to that tail node. Okay, we're going to check if node, if we can get the tail node, then we simply say node dot next is equal to nil. Okay, so we're going to assign that nil for the tail's next node. All right. With that, actually, we can simplify this thing because we're not going to need this for, so we can simply say this right here. Okay. And now we simply say self dot q dot add to head node and self dot hash table. So add that value into the hash table with the key that's provided and the node that is created. Okay, so let's walk over this one more time. So we first went ahead and basically checked if the value is nil. If it is nil, we return from here because we cannot set that. Now, next thing we do is we check the hash table if the key already exists in the memory. Okay, if it is, that means we need to update the value of the node and then move it to the head of the queue and remove it from the middle of the queue if it is there, right? So what we did basically, we first went ahead and checked whenever we are setting a value for the cache. In that case, if the value is nil. If the value is nil, that means we need to return from there because we don't have anything to set. Next thing we check is we look up the item in the hash table and we see if we can find that node being basically stored inside that hash table. If it is there, that means it's just a value change. So we change the value for that node, for that memory address, and go to that memory address and change the value for the node. And then we remove that node from its location and move it to the head of the queue. Okay, so that means because that item has been accessed, we want to refresh it to be like more frequently used than all the other items. Okay, If that is not the case, if we could not find the item inside the hash table, we go into the else condition. We create our node first. We check if the length of the queue is basically less than the capacity, right? So if the length of the queue is less than capacity, then we simply say that, hey, that means if memory limit is not reached and we can still insert an item, so we actually add it to the head, add it to the hash table, increase our length, and then continue forward. Okay. If length of the queue has been reached over the minimum capacity, in that case, what we need to do is we need to first remove remove an item from the hash table. So the item that needs to be removed from the hash table is going to be the tail node for the queue. Okay, and we're going to update the queue, and we're going to say a queue, take your tail node and assign it to the previous value of the tail node. Okay, and if we can access the tail node, so we access the tail node once again and assign its next value to be nil. Okay, because when we have like previous assigned to the tail node, previous is next is still going to point to this old tail node, so we want to make sure that we assign that to nil. Okay, once we have done all that operation, we have removed our tail node, and then we're going to add the queue to add the item to the head of the queue and add basically the hash table. Okay, so basically add that key, that node and key into the hash table. All right, so that is going to take care of our Lru cache's set property. Okay, so let's go ahead and test this functionality out, and what we're going to do is we're going to delete everything that we have, go to our main, and we're going to create our Lru cache. Okay, and we're going to say it's going to be of string, key is going to be of string type, and the value is going to be of int type, size is going to be 10, and we're going to simply say for I in 1 to 11, right? And we're simply going to say Lru cache. Just R and that I to satisfy that this is a string that we are actually creating as a key, and then we're going to simply say I times 100. So we're going to store I times 100 as a value. Okay. And now we're going to print our Lru cache. So we're going to say I in 1 to 11, and we're going to say print values. First of all, print values from the Lru cache. So we're going to simply take this and put it here. Excuse me. And it should print values in our cache. Okay. So let's go ahead and take a look. So we have, all right, so there's expected, fine, Lru cache, Lru cache. Matching, okay. So we definitely made some mistakes somewhere. That's why it's complaining. Consecutive declaration needs to be separated. Lru Node private hash table. Okay. So let's take a look at our hash table wherever we are defining. So Lru.Swift line 58. Okay, so line 58 hash table, Lru Node, that's what we are calling it, and we have our closing bracket. So let's see. We are opening the key, defining the key. Oh, okay. So it's a dictionary. All right. I just okay. So expected comma. Oh, yeah. Okay, so like that. No, actually. Um, so let's see how we can. We need to print this particular expression. Yeah. So we are simply gonna say we need to print this expression. So let's see what it says. And it's gonna complain basically to the cannot call the value of non-function type any. Non-function type any. Okay. Line 65. That's actually line 65 right here. And what it says is basically we are setting Lru Node. Same mistake that I made here. Okay, so it looks like it is actually executing. Okay, there we go. So we are getting our optional values. And as you can see, let me go in the main again. And I'm going to force unwrap this because, oh, it's actually going to crash. Force unwrap is not going to work. Okay, so it's going to come as optional. So if let val is equal to this guy right here. So if we get anything, we actually print val. Otherwise, we simply convert it into a string. Else, we simply print item removed. Okay, so if you notice, we inserted 1 to 11, right? So 100 to 1100, but our cache size is 10. So when we retrieve items, what we retrieved was 200 to 1100. Okay, so our cache size did not increase, and it maintained the priorities and everything. So if you go back to your queue, and I would actually go and maybe print or open the queue actually. Let's print. Can we print? Do we have like a printable queue? We don't have printable queue. Okay. So what we can do is we can simply say func print queue, right? And can say for temp is equal to head node self.head node. Well, self.head node is not equal to nil. Okay, we are well, temp is not equal to nil. We're gonna say print temp dot value, right? And temp is equal to temp dot next. Okay, so this should print our queue. So let's take our queue and make it publicly accessible for now. And let's see if we can print our queue here. So print Lru Cache dot queue. Not print queue. I think that's the function name. Print queue. Okay, so we're gonna print our queue. So let's take a look if we can print our queue. And what we should do is all item removed. It's not printing anything because I think we made a mistake. Print queue. So tick temp head is not nil. So basically, when we try to print our queue is not getting printed. Excuse me. So our queue is not getting printed. Now the reason for this is because if you go back to our queue and if you take a look at our cache, basically where we are setting the queue is this is where we are actually inserting our queue, and this is an async operation. So what happens is basically this is asynchronously executed on a different thread, and that actually causes other threads to start the processing. So what we need to do is we need to change this to sync and go ahead and execute then. And you're going to notice that your queue is now getting printed because that operation is sync. So if I go back and uncomment this code, we're going to see our queue. This is our queue that's getting printed, and this is our once again, this is our cache, and this is our queue. Okay, and if I access an item, for example, let's say if I access an item here, so maybe val or say print this maybe R2, right? So R2, we're going to access that and we're going to print it. And after that, if we print our queue once again, or R4, let's do R4, and then print our queue again, you're going to see that R4 is going to be printed as the head of the queue. So let's go ahead and take a look. Okay, so this is our queue before when items got inserted, right? These are all the items that are in Lru Cache. This is what we printed, access for 400, and as you can see, our new head is now at 400, right? So we have 400, then 1100, 1000, 900, 800, 700, 600, 500. 400 is moved from here and jumped ahead of the queue, 300 and 200, because we accessed that particular element. So that's what the basic operation of Lru Cache is. So hope it was clear. I know this was a rather long discussion or a rather long answer, but I want to make sure that you understand each aspect of Lru Cache because it's such an important question, and it's actually very frequently asked question if you count any programming interview. All right. So with that, we have reached to the end of this video. So thanks again for joining me here to look at this awesome problem and solve this together. And I will see you guys in the next video. Thank you.